Good afternoon, everyone. So, I would like to thank Dr. Alexander for presenting the UTT part of the study, and I will now present the part that was conducted by the UWI. So, the UTT, the UWI is also responsible for certain fields in the Southern Basin onshore 2 fields, uh, offshore 3 blocks, and the Columbus Basin 4 fields. The UTT developed the calculator for doing the volumetric calculation, and we developed the workflow for determining the parameters that are required for the calculator. So we use students and graduates were contracted to work on the storage atlas project so as to build local capacity. More data is needed to estimate full storage potential of the reservoirs. Shell has partnered with us since 2022 and has provided funding support. Woodside Energy is expected to come on board soon. And we are also planning a CCUS symposium in 2024. That will be April 25th and 26th. So keep a note of the date. Data were obtained, but not as timely as expected. The data was screened and cataloged, and complete data sets which were not available, we use offset data and analog data. So there are future opportunities for UWI and UTT, which include collaboration between the CCS and the CO2 EOR working team, development of carbon and gas management programs and courses, and the establishment of a center to drive relevant projects to develop a proposal for a pilot CCS project and to also conduct combined projects, for example, blue and green hydrogen and direct air capture. So we also would like to also have programs, short programs and full MSc programs to be delivered by that center. So I will now move on to the next part of the presentation, which is on the hydrogen part. So hydrogen can occur naturally as a pure gas. However, it rarely exists on its own and is commonly found with water and methane molecules. Sorry. There are 2 main ways to extract hydrogen, and these have been presented by previous presenters. Electrolysis using electricity to separate the hydrogen and oxygen ions in water, and also methane reforming, in which steam and methane and sometimes oxygen are reacted at high temperatures and pressures. The water required has to be of very high quality with low concentration of salts and minerals. The water must also be equivalent to or lower than potable water, and such high quality water is scarce and has increasing demand for domestic needs. And this data was also presented by one of the students. The demand for hydrogen was estimated about 90 million metric tons in 2020, and the amount of CO2 released was about 900 million tons of CO2. This CO2 can be captured and stored. Now, gray hydrogen can be transformed into low carbon blue hydrogen by capturing and storing the CO2. In Trinidad and Tobago, methanol and ammonia are produced by the steam methane reforming process. Now, we have seen green hydrogen and blue hydrogen, how it is produced by the steam reforming process. And green hydrogen can be produced from wind or solar energy, which provides the electricity for the electrolysis process. Now, alkaline water electrolysis have some advantages over proton exchange membrane electrolysis. So from studies conducted by the department, we have showed that wind energy to be the most favorable form of renewable energy to provide electricity for green hydrogen generation by alkaline water electrolysis for Trinidad and Tobago. And we can obtain green ammonia and green methanol using wind energy and the electrolysis of water. So looking at this slide, Proman North Sea Methanol Project is the first large-scale renewable hydrogen to methanol complex of the North CCU hub, and this has been established in Belgium. And we also see that green ammonia facilities are being developed in South Australia, the United Arab Emirates, and South Africa. Now we have seen that water is essential for hydrogen production, and over 2 billion people live in water-stressed countries, which is expected to be exacerbated in some regions as a result of climate change and population growth. Globally, at least 2 billion people use a drinking water source, which is contaminated. Hydrogen project developers and the water sector must consider sustainable water sources such as desalinated, recycled water, and storm water to offset the demand for fresh water and to avoid exacerbating water stress. Irrespective of the source, the feed water must be cleaned and deionized, taking into account water losses due to evaporation and leaks. The water ratio can range between 18 kilogram and 24 kilogram of water required to produce 1 kilogram of hydrogen. The public water system in Trinidad and Tobago are supplied by surface water from rivers, dams, and rivers, about 60%, groundwater from wells, about 23%, and desalinated water, about 17%. In Trinidad and Tobago, we do not have a regular supply of water for domestic use. We have 3 municipal wastewater treatment facilities for water reuse. These treatment plants are located in the north, south, and east for the Spain, San Fernando, and Malabar Arima area. So in the wastewater treatment facilities, there are many processes that are involved, and I will not go through these processes in the interest of time. From the south plant, we did do an analysis of the water content, the pH content, the total organic carbon content, the chloride, ion, and fecal coliform count were measured, and they were found to exceed the ASTM specification of D1193-06 type 1 grade for reagent water. And what we looked at is an advanced treatment of the tertiary effluent, and that is recommended to produce the water required for the use in the electrolyzer. Preliminary cost estimated were prepared for the required advanced treatment, and the total is about 85.6 million US dollars. 2 water rate scenarios were considered for hydrogen production. The current is $3.50 per meter cube, which is industrial rate, and a higher rate of TT $5.50 per meter cube to achieve capital cost recovery within 10 years from the start of producing high purity water. The cash flow projection for the advanced treatment commenced in 2024, which with the capital cost for design and construction evenly distributed over a 6-year period. The start of high purity water production coincide with the projected start of the hydrogen production, which is in 2030. And from then on, the cash flow projections span 30 years from 2030 to 2060, which is considered a reasonable life expectancy for an advanced wastewater treatment plant. And with the current industrial water rate of $3.50 TT, positive cumulative cash flows is expected from 2051, reaching $38.5 million by the end of 2060, with a payback period of 28 years and an internal rate of return of 2.22%. At the high water rate of TT $5.50 per meter cube, and to recover capital costs within 10 years will lead to a positive cash flow from 2039 with a shorter payback period of 16 years and a higher IRR of 7.9%. And by the end of 2060, the cumulative cash flow will reach $186.6 million. Further analysis has shown that purchasing desalinated water was not viable due to the negative NPVs and no IRR at both water rates. So this is the end of my presentation, and I would like to acknowledge the Ministry of Energy and Energy Industries, Heritage Petroleum Company Limited, De Novo Energy, BPTT, Shell, for the funding support and data that has been provided for conducting this project, and also Ms. Amanda Hendy, who was an MSc student in the Department Petroleum Studies Unit, for the study she conducted on the hydrogen part of this presentation. Thank you very much.